Today I'll be talking about linear control design with input constraints. It's an implementation of this paper, Thrust Mixing, Saturation, and Body Rate Control for Accurate Aggressive Quadrotor Flight by these authors. So as an overview, I'll first discuss motivation for the paper and this project. We'll talk about the system definition, the equations of motion for their system we're looking at. We'll then go into the LQR controller design, and we'll talk a little bit about some implications of the LQR controller design. Then we'll talk about two important contributions of the paper, an iterative mixing scheme and a prioritized input saturation scheme. We'll talk about how what I did to implement this work, and then we'll talk about some future work items. So as motivation, we like linear systems. We often, well in this class especially, we've taken nonlinear systems, linearized them, and done some nice analysis on the linear systems. But the question is, what happens if the input command has limits? So one implicit assumption in the equations above are that our input just kind of extends on forever, and we can actuate as hard as we want to compute the command that we want. But in real life, actuators have limits, and so you get this saturation region, which leads to inherently a nonlinear system. So takeaway is, even if the system can be accurately linearized, if your equations are, even if they're linear equations, if you have bounds on your input, you're not going to be able to track all the controls that you would like to track. So the objective of this paper is to develop a method to handle input saturation in an intelligent way that still maximizes use of the full actuator range. So we want to be able to handle aggressive maneuvers, aggressive trajectories, but we want to handle saturation in a smart way so that we can still have some guarantees on our system. So let's talk about the system. So we're going to talk about a quadrotor in this project that has the dynamics listed in 1 through 4, where equation number 1, eta, is our body torques, so roll torque, pitch torque, and yaw torque, and it's a function of F1, F2, F3, and F4, which are the forces produced by each rotor. That third equation has some kappas in there. The kappa is the rotor torque constant. It just translates your force to your torque. So given a force that your propeller is producing, kappa turns it into a torque. Number 2, C is our desired mass normalized thrust. So we take C, we multiply by our mass to get our total thrust, and it's just the sum of all the forces from each rotor. We have equations for our angular rates and the derivatives, which are functions of the inertia matrix and the angular rates, omega, as well as the body torques. And then equation number 4 describes a first order response of our motors and propellers, essentially. It's just describing if you get a command, it takes some time to spin up to the speed, to the desired force. They model that as a first order response with a different time constant depending on if you're going up or if you're going down. So some details about the force and torque, I'm going to kind of skim over this, but the important thing to know is equation number 7, where kappa is a function of your force. So the torque constant is a function of your force. That's important because it turns out that you can't directly solve equation number 1 and 2 for F1, F2, F3, and F4 if you're given a desired eta and a desired C. You just can't solve for it since kappa is a function of F. So we're going to have to do this iterative mixing scheme, which I mentioned earlier, in order to accurately do that. So now let's move on to the LQR controller design. So steps, we're going to first gather nonlinear equations. We're going to make some assumptions in order to linearize the system. Then we're going to compute our K-gain matrix and make some interesting observations. And then we're going to add some feed-forward terms so that our controller has some nice properties associated with it. So we're going to define our state, S, as omega and eta, which are body rates and our body torques. We're going to define our input as our desired our desired body torques. And we're going to assume that alpha is the same. And then we're going to also assume that kappa is a constant so we can linearize our system. We won't make these two assumptions later, but for now, in order to linearize our system, we're going to make them. So if you make those two assumptions, then you can arrive at equation number 8, which is our x dot equals ax plus bu, which are our linearized equations of motion of our system. Great. So now that we have A and B, we can compute our LQR gain matrix as we talked about in class. where K is equal to R inverse BT, B transpose P. And we can define our U to be equal to negative KX. And now in equation number 9, we've thrown a lot of terms all of a sudden. First thing to note is that we've added an omega desired, so desired angular rates. And we've done that because we don't want to drive our system to 0. We want to drive it to the reference trajectory. So that's the reference term that we're tracking. The eta ref is calculated from omega desired. And yeah, so that's how we get that first part of equation number 9. The second term on the right-hand side of equation 9 is a feed-forward term or a feedback linearization term. And same with that third part. Adding those feedback linearization terms, that third one is optional, but adding those in has the nice property that when omega equals omega desired, we also have that omega dot equals omega desired. I'm going to skip over some of the details here, but just know that this controller has some nice properties associated with it, in addition to it being a nice LQR controller. So a side note about the LQR gain matrix K, because of the structure of our B matrix, we actually have that our K kind of has this form on that third row where where it kind of looks like a PD controller, where each axis of our system, the X, Y, and Z, has two gains associated with it, and they're all independent of each other. You've got one on the omega and one on the eta, and that's it. And that just pops out from the structure of our B matrix. In our controller, we also changed our omegas to omega hats. So we have to have an estimator that can estimate omega hat and eta hat. The paper recommends that you use equations 4 and then plug it into equation 1. I didn't find that was super reliable. There's a different method that you can use to do that. Technically, from just rate gyro sensors, which measure your roll rate, pitch rate, and yaw rate, the whole system is observable since you can form your C matrix as shown, since we can directly measure omega. And it turns out your observability matrix has full rank. So your system is observable. You can observe omega and eta. In the simulations that I did, I just assumed that those were given, and I used the truth values. So let's talk about the iterative mixing scheme that I talked about earlier. I'm going to gloss over this a little bit. I didn't end up using this scheme for reasons I'll talk about later. But the point of it is, again, since kappa is a function of F, you can't directly solve for our forces. So what you do is you initialize your forces, you solve for kappa, then you use that kappa to solve for the forces, then you iterate. Then you plug those forces back in to solve for kappa, and you just iterate until your forces converge. Usually takes like 3 or 4 iterations, according to the paper. So now let's talk about the more interesting contribution of the paper, which is the prioritized input saturation. So again, we want to operate on this realm of, we want to push our aggressive capabilities while still maintaining saturation of the parts we want. So that leads to kind of this intelligent saturation scheme, this prioritized input saturation. The key realization is that some directions are more important than others for safety. So for quadrotor specifically, we really care about the thrust direction, because we can only fly in the direction that we're thrusting. And so we really care about that direction, but we really don't care about the angle, the yaw angle around that thrust direction as much. It can be important, but if something has to drop, then we'd probably rather drop the yaw than the thrust direction. So we can define this prioritization scheme where we want to prioritize the thrust direction and then the total thrust and then the yaw, the torque. So if we can meet all three, we'll meet all three, but if we can't meet all three, then we'll drop off yaw first. And if we can't meet the thrust direction and the total thrust, then we'll drop off the total thrust. We'll be left with the thrust direction. And if we still can't meet the thrust direction because our motors are saturating, then we're just going to have to cut our losses. We'll clip the forces and just move on. You can't do better than that. If your desired forces are too high, you're gonna end up clipping your thrusts. But using this scheme, we can there's a lot of those intermediate cases where we can do intelligent things and have some pretty nice results, as we'll see later. So in my implementation, what I did is I implemented LQR from scratch, including solving the ARE in a C++ ROS2 node. I implemented the iterative mixing scheme, and I implemented the prioritized input saturation scheme. I simulated it all in a quadcopter and gazebo using the Rosscopter framework. and then I compared different controllers to examine some of the different properties between them. So now some assumptions that I made, in addition to the ones in the paper, I assumed the cap was a constant. I didn't have the data that I needed to compute the cap as a function of f, so I just assumed it was constant. And I also assumed that some estimator could give us eta hat and omega hat, so I just used the truth values. So here's a little diagram. I'm going to skim over this, just showing how information progresses through the system. In my simulation setup, I compared 3 different simulators. That's what this is showing. On the top one, I got the full LQR design with the prioritized input saturation. The middle one, I just removed the input saturation to kind of compare what that input saturation scheme does to our system. And then I finally compared that to a PID control as well. So I ran 2 experiments. One, I did a disturbance rejection where I applied that disturbance at that location, and I compared the PID with the LQR control. And then I also did a simultaneous altitude and heading step input. Now this one's interesting because it kind of excites that mode of this system. It shows us why the input saturation scheme is necessary. So if we look at the disturbance rejection plots, these plots are small, I apologize. What's plotted is the northeast down position in meters. So on the right, we have the PID, and the left, the LQR. When I apply that disturbance, and each of those spikes is a different time that I applied it. So I applied it on the left 3 times and on the right 6 times. One important thing to note is that all 3 axes of the PID control kind of get driven away from their desired location, while the LQR is able to control a lot better. So takeaway, LQR had better recovery after disturbance. PID could probably be improved if you had better tuning. Now the more interesting one is the altitude and yaw simultaneous step inputs. Now this is interesting because again, it kind of excites the mode that we're interested in looking at. So if you look at the PID one first at the far left, you'll see kind of stair steps. And as a background to these plots, the blue line is the altitude input, the true altitude state, and the red line is the yaw state. And so what I did is I commanded a 1 meter increase in altitude, and then I dropped it back down. And at the same time, I did a 90-degree increase in yaw, and then back down to 0. So in all 3 of these plots, you'll see a step up and then a step down. So the yaw one has an interesting kind of stair step approach, and you'll notice that happens at the same time that we're trying to yaw. So it kind of shows that the 2 controls are fighting each other, where you since as you yaw, you have to speed up some motors, and so you end up moving faster than you'd like. And so you get this kind of stair step where your controls are kind of fighting each other. The LQR and the LQR without input saturation perform very similarly, except for on the step down. So in the middle of the plot, in the middle plot, you can see that when we step down from 1 meter down to 0 meters, and from 90 degrees yaw to 0 degrees yaw, we have this big step, big jump in our altitude command. And that's due to the fact that when you yaw, you have to speed up some motors, and so the drone actually flies up before it can drop down. Whereas with the input saturation scheme, we don't have that. So kind of shows that it's useful. And the LQR with input saturation performed better. And you probably see more improvements if you had an even more aggressive trajectory that required more saturation. So some future works listed here. The one that I'm interested in is adding different motors, adding more motors. Since more motors means an overdetermined system, so you have some ambiguity, I guess, like what's the best way to prioritize that input saturation scheme? Which motors do you saturate first? What order do you do it in order to intelligently saturate? Anyway, so that's all. Here's the references I have. Thank you for watching.